So this is E658 lecture 20. Yesterday we were looking at the spectra of quantized signals, and this is where we left off. The blue sine wave is the ideal sine wave. The red step-like waveform is the same sine wave quantized with a step size of 0.1, and the blue guy shown here is the quantization error. And we were trying to build intuition yesterday onto about why or how the quantization spectrum should look like. One piece of intuition we got was that if you kind of stare at this waveform, you can see that this looks like some kind of FM waveform with some average frequency, and we counted the number of times this triangle jumps up and down, and we kind of said that this must have a significant harmonic content around between about 45 and 55 or something. And lo and behold, when you do the Fourier analysis, you get that's what you see. Please note that what we are computing here are the coefficients of the discrete Fourier series. But if the input sine wave is very, very slow compared to the sampling rate, the coefficients must be at least the first few harmonics must be almost the same as what you would get if you expanded this continuous time waveform in See, in MATLAB I can't have continuous time. So what I do is, you choose a frequency which is low enough. In this particular example, I've chosen Fn is Fs by 1024. So, and I've taken this discrete time sine wave and computed the coefficients of the discrete Fourier series of the sine wave as well as its, quantized counterpart. And all that I'm saying is that if the input frequency is very, very small compared to the sampling rate, which is certainly true in this particular example, then the coefficients of the sine wave of the discrete Fourier series that you get when you expand this discrete time periodic sequence in a Fourier series will be very, very similar to the coefficients you get when you compute the continuous time Fourier transform. The continuous time Fourier series of assuming this is purely continuous time. So this is pretty much what you can expect the first 100 harmonics or so of the continuous time Fourier series to look like. And as you can see, there are spikes. Some spikes are larger than others, and if you actually plot all the stuff up to 512, you'll find that in general the higher order stuff harmonics amplitudes are reduced. To gain some more intuition, let's see what happens when I take the same sine wave and I've now quantized it with a step size of 0.2 rather than 0.1. This is again Fn is Fs by 1024 as usual, and the step size is now 0.2 rather than 0.1. In other words, the step size is increased by a factor of 2. So what would you expect the Fourier series of the when I do the Fourier transform of one point is definitely the peaks at which the harmonics occur should lower, right? Why? Because the time period is less, definitely, right? Because the step size is more. So to get to hit the next level, it takes a longer time. And this waveform therefore is a lower frequency waveform. Within quotes, this is also full of discontinuities. So in principle, both the previous quantization error and this quantization error all have infinite continuous time wave both of them have got infinite harmonics. But as they keep saying, some people are equal and some people are more equal than others, right? So similarly, this is another case where this has also got discontinuity, so in principle this is also got infinite bandwidth, but you can see that this is dilated in time, so it must be compressed in frequency. So you can expect the peaks of the harmonics to kind of fly at around 1/2 of what you saw with the earlier case. Yesterday we saw around with the earlier step size of 0.1, the peak was occurring around here. With this step size, you can see that the peaks have. Another interesting observation is, so this I will write. Now can somebody give me a quick and dirty estimate of where this peak is going to lie in general for a sine wave of amplitude A? So, if you're sufficiently drunk, you can approximate the sine wave with a square. If you have a ramp, in 1/2 cycle, this is A. If this is A and then you have, and the LSB size is delta, the number of cycles is, the sawtooth is A by delta, times 4 is the number of cycles in the entire sine wave. So this is 0.2. The amplitude of the sine wave is 1. 1 by 0.2 is 5. 5 times 4 is 20. And not surprisingly, okay. And of course, if you want to nitpick, you can see that it is somewhere between around 25 or so. Alright, so the last piece of intuition is gotten by looking at both the plots on the same graph. Alright, this is for a step size of is 0.1, step size is 0.2. And the first thing you must do when you compare two graphs is to plot, is to have the same axis on both the graphs, so that you don't get fooled into deriving intuition for results that don't exist. So I plot both the axes are the same. Now we've already explained away this phenomenon. So this peak occurs around here, this peak occurs around here, and we know why that happens. The next thing is to figure out, if you look at the amplitude here, can you kind of make a guess as to the difference roughly is? It's about 10 dB or so. Let's see why this makes sense. The quantization error waveform corresponding to this spectrum is like this. Stuff like that. Whereas this will be twice as large and half in frequency. If this was, I call this a peak to peak amplitude of delta, this must be 2 delta. That's one thing. And before I get there, let me ask you a quick question. If I sum up the amplitudes of all these harmonics, if I add up the powers of all the harmonics other than the fundamental, what would I get? If I added the powers in all the sine waves other than the fundamental, I should get delta square by 12, because by Parseval, the power, whether you compute it in the time domain and the frequency domain must be the same. We know that the power of the quantization noise is delta square by 12. It must be the same as the power as computed from the Fourier series. One common mistake made by a lot of engineers is to, when given a graph like this and asked to estimate the resolution of the converter, what do you think the resolution of the converter, how will you determine, if I gave you this graph and said, find the resolution of the converter. This is a Fourier series of something I got by taking a sine wave and quantizing it to some bits. Can you tell me how many bits are there in the converter? You know that the peak signal to quantization noise ratio for an n-bit converter is 6n plus 1.76 dB. So if I know that this corresponds to the full scale sine wave, and if I find the signal to noise quantization noise ratio from this spectrum, which is easily doable, I should be able to get the signal to quantization noise ratio in dB, from which I can go and back calculate n. So how will I find the signal to quantization noise ratio from this graph? From this picture, from the Fourier series coefficients, you'll be able to figure out the power in the fundamental, and then you add up the powers, not just the amplitudes, the powers of all the things other than the fundamental. The ratio of the two must give you 6n plus 1.76, so you can find the number of bits n. A common mistake made by a lot of people is to look at this diagram and say, oh, this is 50, this is 10, so the difference is 40 dB, right? So 40 dB divided by minus 1.76 divided by 6 should give you the resolution of the converter. That's clearly erroneous by a large margin, simply because if you consider only 40 dB, if you consider this to be 10 dB, that's only this harmonic here is 10 dB. If I add up all this, there's a lot more harmonic power, noise power than just this peak here. So that will give you ridiculous answers. So let's get back to this, and we were trying to figure out why this. So clearly, if I draw a cleaner picture, it seems as if the difference is not quite 10 dB, but perhaps a little lesser. Anyway, let's try and figure out why. If I know the spectrum of this chap, what all transformations should I use to get to this kind of waveform? Amplitude scaling and time scaling. Okay. So the amplitude of this chap is 1/4 the amplitude of this guy is 1/2 the amplitude of the guy on the right. So the power must be 1/4. 1/4 is only 6 dB. But the other thing is that this waveform is twice as fast as this waveform. If this is some E of t, this is basically 1/2 E of, intuitively speaking, if a waveform is scaled in time, what can you conclude about its frequency content? If it's compressed in time, the frequency band must increase. If this waveform had, say, m significant harmonics, where significant harmonics means where most of the power is concentrated, how many significant harmonics will be in a waveform which is compressed by a factor of 2? It's twice as fast. So you need, loosely speaking, you need twice as many harmonics to get twice the slope. But the power in both these waveforms, E of t as well as E of 2t, must be the same. Right? The mean square value of this noise, this quantization noise, must be the same in both cases. I mean, if you forget this half, if I scaled this waveform up by a factor of 2, then the power in this waveform and the power in this waveform here must both be the same, and that must be equal to 2 delta the whole square by 12. The only difference is that this is now moving at a rate which is twice as fast. So there will be, the same power must be distributed in twice as many harmonics. So what can you say about the peak harmonic? It should reduce by a factor of 2. So the amplitude reduction by a factor of 2 will give you a power reduction. So amplitude reduction will give you 6 dB, and the same power, or time compression I must say, will give you an additional factor of 2 in the power, so it will give you 3 dB. And as I said, intuitively the way to understand this is that the quantization noise waveform is scaled by a factor of 2 in amplitude and compressed in time, roughly speaking. So the same energy must be concentrated over twice the number of harmonics, so you can expect the harmonic power to fall totally. So increasing the ADC resolution by 1 bit causes the peak harmonic amplitude, amplitude goes down by a total of 90, which is roughly what we see here. So this is an important thing to know, simply because of the following, which is that when you build an A to D converter, this is your desired tone, right? This is the input. Let's say this is your desired input. All these guys are undesired and are often called spurious tones. This here is what is called the spurious free dynamic range, or the SFDR of the A to D converter. Right? This is also often quoted metric when people make and sell A to D converters. They will also quote the so-called spurious free dynamic range of the A to D converter. Why is it important to quote SFDR? Okay. The spurious free dynamic range becomes important in communication applications. For example, let's say you're trying to digitize a channel. You know that in most of your, in all your handsets, it is not, your desired channel is only very small, and GSM is 200 kilohertz. But what you do is, at the A to D converter, in the analog front end, you cannot digitize, you cannot have a filter with such low bandwidth. The channel is 200 kilohertz sitting at a center frequency of 1.8 gigahertz, right? So it's impossible to build an analog system which will filter off everything other than the desired 200 kilohertz. So what is commonly done is you digitize the entire band, maybe consisting of 16 or 20 channels, and do the channel selection, which is pick out the particular channel in that full GSM spectrum in the digital domain, where it's very easily possible to build very sharp digital filter. If your desired, so you're trying to digitize this signal, something like this, and if your A to D converter itself is adding spurs like this, then the spur can be mistaken for some, for a channel easily, and that can degrade the performance of the receiver. So the spurious free dynamic range is often a spec in communication receiver. So the Nyquist, a Nyquist tone is the worst case example for the input tone, and typically spurious free dynamic range is quoted with a tone close to Nyquist. The important thing that comes out from this discussion is that even if you had an ideal quantizer, if you increase the resolution of the converter by 1 bit, the signal to quantization noise ratio goes up by 6 dB, but the spurious free dynamic range goes up by 9 dB. So signal to quantization noise ratio goes up by 6 dB, and the spurious free dynamic range goes up by 9 dB. And this is theoretical stuff. In practice, okay, because of various other non-idealities in the way you implement the converter, adding this extra bit may not improve things by as much, but this gives you an upper bound on what you might be able to achieve. As I said, this in a practical A to D converter, of course, the step size will not be as large as 0.1 or 0.2 for a sine wave of peak amplitude 1. Typical resolutions are 6 bits, 7 bits, 8 bits, 10 bits, 14 bits, that kind of thing, again depending on application. This is a 10 bit A to D converter with an assuming ideal quantization levels, and again, as I said, this is the DFT. One half of it is symmetric, it can be gotten from the other half. So the unique part of the stuff is only this picture here, and as you can see, this is a 10 bit converter, so how many levels are there? 1024, and what spurious free dynamic range would you expect? You would expect about 90 dB, so which is roughly what you see, right? This is about 54, and somewhere around here I would think, which is about, I'm tempted to say 36, but it's probably around 30 dB or minus 30 or something like that, certainly minus 35 or something, right? So this is an ideal quantizer, and you can see that the SFDR is about 90 dB. In practice, there will be non-idealities. For example, the sample and hold might be distorting, in which case you will see all this is quantization noise and this is distortion. In this example, the input was the sample and hold transfer characteristic y is not the same, is not equal to x, but x minus some point, I think 0.001 x cube. And this is an odd order nonlinearity, so you would expect only to see only odd harmonics. Alright, so this you can see that this has got the fundamental and this is the third harmonic. And the spurious free dynamic range in this case is clearly 54 and about 20. This is only the aim behind this example is that the quantization noise in most cases doesn't limit your spurious free dynamic range. It is other effects, non-idealities, which come in, which will almost always limit your spurious free dynamic range because sample and holds distort, and all the SFDR theory that we saw was for uniform quantization levels. In practice, it turns out that the width of the bins due to analog imperfections, the width of all the bins will not be identical and equal to 1 LSB. Some bins will be smaller, some will be larger, which basically means that the DNL and INL of the converter are not identically zero, in which case, depending on the details of the nonlinearity, you will definitely see spurs. But one other thing you can observe from here is that if the number of levels in the converter are very, very large, you can see that the spectrum kind of looks, the peaks kind of all, so this is certainly not a justification, but this is just to show you that the white assumption may not be all that bad in fact. And as it turns out, it's a very good assumption. Alright, the last remark about quantization noise is the following. So you can, what we're trying to do is find the spectrum of this signal here. So this is x of t, this is y of n. To understand the spectrum of y of n, it hardly matters whether you sample first and quantize, or you quantize and then we just saw what will happen if if I put in an input tone x of t, right? So the spectrum of that will be something like this. If I looked at this waveform here, I will get harmonics. Now, when I sample, what happens? I mean, the quantization error has got some steps, right? So, in principle, all harmonics right up to extending all the way up to infinity exist in this spectrum here. If I compute the continuous time Fourier series here, this is roughly what I would get. The moment I sample it, what happens? Everything beyond fs by 2 will alias back. So, if this is fs by 2, all this stuff gets back. And this, I mean, if you take some random stuff and then all alias back, that's one reason why, even though the Fourier series of the continuous time stuff looks like this, when you kind of add everything up, you get this kind of gets filled out, and it looks more or less kind of uniform. So just to give intuition, there's nothing majorly, there's no rocket science here. So the key things you must know are, given the spectrum, you should be able to find the resolution. You should be able to look at the spectrum and tell me what the spurious free dynamic range is. The same considerations that you use to choose the input frequency relative to the sampling rate must also be followed. I mean, the same considerations which you use when you design this and can characterize the sample and hold must also follow here. So, you must choose again Fn to be equal to some capital M by M times Fs, and M is some 2 to the power L, and M is relatively prime to, you can choose M to be a prime number, and in which case the periodicity of this whole thing will be, the record will be periodic with a time period of M by Fs. So that finishes the discussion on quantization, at a high level, in the sense that we know roughly what to look for. Now the real thing is to try and implement the quantizer, and as you have guessed, there are many ways of implementing a box which can take an analog input and classify it into different bins. The cheapest thing or the simplest thing I can think of is the following, which is, we have this analog input, let's assume it is held. What do I do? One way is to compare this input with a simple, cheap, straightforward way is to generate. Okay, so I know that I must classify my input and figure out whether it lies in which bin it lies, where the bins are, say, vref 1, vref 2, all the way up to vref 2 to the n minus 1. So a straightforward way of doing it is to compare the input simultaneously with a whole bunch of references, the references being chosen so that they are all uniformly spaced within the full scale range. And this guy here is not to be confused with an op-amp. This is called conceptually, this is the job of this chap, is to is to compare Vin and Vref and say out is equal to 1, a digital logical 1, if Vin is greater than Vref, and is 0 if Vin is less than or equal to Vref. It doesn't matter where you put the equal to sign, because in practice Vin will never be equal to Vref, right? Because there is always noise riding on Vin and or Vref. Such a block, so the basic building blocks is what is called a comparator, and the defining equations for the comparator are this. So without knowing anything, if I mean, you can definitely say that if I had a comparator, if I had a black box which is capable of giving me a logical 1 if Vn is less than if Vn is greater than Vref, and a logical 0 if Vn is less than Vref, then I can take many of such black boxes and connect them up to different references, okay, Vref 1, Vref 2, blah blah blah, all the way up to the last reference, and to their positive terminals I connect Vn, okay, and looking at the outputs of these guys, I should be able to figure out in which bin the input lies. This is the principle of what is called, this way of doing A to D conversion is what is called a flash analog to digital converter. So since everything is going on in parallel here, alright, this the performance of these converters is the fastest. So when you want the answer in a flash, you use a flash converter, okay, and as you all, I mean, as in general, you know that when you're doing things quickly, things are not efficient, which basically also means that power and area wise, this is not the most efficient way of doing things. But in some cases, it's absolutely essential to have a very, very quick result. An example of such converters is things where you have a very high speed feedback loop, which happens all the time in in communication and control. So when you want to have very quick, when this AD converter is embedded as a part of a feedback loop, you can't, in a feedback loop you can't wait for because the loop will go unstable. So when this is embedded in a feedback loop, when you want things done quickly, that's when flashes are used. So and when you so typically flashes are always the first converters to be done in in any advanced technology. So as technology keeps advancing, right, data rates, for example, your disk drives, the data rate being read out of the disk is being read at several gigabits per second, and the de facto choice of the AD converter is a flash converter. So if you see the advances in flash converters, you will find that most of them are all from the ICs designed for disk drive read electronics, where the speeds at which you read data off your hard drive are keep increasing with time. So 10, 11, 12 years ago when I was working on this stuff, the speed was like about 700 megabits per second. Today the speeds are close to 2 gigabits per second. So you can see that there's a 3x improvement in speed being in data read speed. Okay. So to give you a simple example, if this was the full scale range, so this is reference 1, Vref 2, Vref 3, Ref 4, 5, 6 and 7, okay. This is the full scale range. So can somebody suggest a way of simply generating these references given the full scale voltage? The intuitively straightforward thing to use is to use a resistor divider, and that's what is done a lot of the time. 8-bit example, in a 3-bit example, we need to classify the input into 8 bins, and what is the topmost reference? It will be Vref 7. And so each of these references goes to this black box, which we call a comparator, which will figure out, the next thing is to figure out how to generate circuits which will do this operation for you. But for the time being, so this is comparator 1, this is comparator 7. So in general, for an n-bit flash, you need how many comparators? 2 to the power n minus 1. So as you can see, the complexity of the flash converter is exponential with the number of bits. And that intuitively makes sense also, because you know that dumb search is the dumbest thing you can do. It follows that it is exponentially complicated. Doing a dumb thing is not too bad if the n is small. So if you have only 4 bins, it doesn't make sense to write a big program to do bubble sort, right? When you can just go and look into the 4 bins and figure out where the input signal is. So similarly, for low resolutions, a flash is not too bad of a solution, but it becomes increasingly painful as the resolution goes on increasing. So typically, flash converters are restricted to, if you want 6 bits, a flash is not a bad idea. If you want 6 bits and you want it now, a flash is the only idea. And thankfully, in most systems, practical systems which require this kind of speed, 6 bits is adequate. You'll see if you kind of go rummage through the journals, you'll find any number of 6-bit flash converters. You'll never find a 10-bit flash converter, because it becomes completely, is very, very inefficient for both power and area. One issue is the implementation complexity. And so if the input lies between, say, the input lies here, that is between VREF 6 and VREF 7, what will be the outputs of the comparators? What will this comparator give you? The lowest one? It will give you a 1, blah, blah, blah. What about this guy? 1. What about this guy? So the output of the comparators will be a sequence of all 1s followed by a sequence of all zeros, where the transition occurs is the, in that bin is where the signal lies. So I think I'll stop here. We'll continue tomorrow.